So, welcome back. So, as you have seen, very exciting things happening in turbulence. That is, so turbulence, the whole mechanics works like this, that the mean or the energy of the mean flow, the kinetic energy of the mean flow is taken away, and that is used for creating turbulent kinetic energy. Okay, and that clearly shows up in this equation that you have seen that the transport equation for the transport equation for the kinetic energy of the mean flow, and the transport equation of the turbulent kinetic energy, where P was appearing as a sink term for the former and as a source term for the latter. And of course, this is happening through this production, which contains the Reynolds stress times the mean velocity gradients, and then it is happening. Then it is dissipated at the small scales by this thing, which is the dissipation rate, turbulent kinetic energy dissipation rate. But how does this happen? Okay, for that we need to go into the turbulent scales and energy cascade. So, as you have seen that from the jet image itself, from the turbulent jet, is that the turbulent motions range in size from length scales compared to the order of comparable to the flow length scales. That is, the flow length scales can be for a jet, can be the width of the jet, to the size orders of magnitude smaller. Okay, to the size which is order of magnitude smaller. So, the smallest scales, if you have a jet like this, okay, the largest eddies you will see is basically the essentially of the order of the size of the jet. Okay, but the smallest eddies, this then becomes actually cascades into smaller and smaller eddies, and these smaller eddies are actually much smaller. So, if this is of the order of say 10 centimeters, or this largest eddy for a jet, then this can be of the order of few microns, given the Reynolds number, of course. Okay, so that is how this thing happen. How does the turbulence convert this energy that is coming into the large scales, and how is that going into the small scales? So, that is the whole concept of this cascade. Okay, and the smallest scales at which this the smallest scales of turbulence will be called the Kolmogorov microscales, which will come later. So, and as you have seen that just from the image, from that the jet image, we have seen that the scale separation. What do you mean by scale separation? By scale separation, we mean that the we can say that the ratio of the largest scales of turbulent motion to the smallest scales of turbulent motion, and that increases as Reynolds number increases. Okay. So, what happens is that, so at the largest scales we have this, say if this L is the largest scale, okay, and say this is the smallest scale. So, at the largest scales we have the energy containing range. Okay. So, where the energy is essentially injected, okay, where the turbulent kinetic is injected by the production mechanism, and then it basically travels through a whole range of scales, through this range of scale called the inertial subrange, which is essentially, we will show that is universal in nature, and until and unless it is dissipated into this dissipation range, for the smallest scale will be the eta. Okay. So, this demarcation between the energy containing range and the inertial subrange, we will call this as LEI, and the demarcation between the dissipation range and the inertial range will go as LDI. Okay. So, that is how the definitions go. Okay. Now, kinetic energy, as we have seen that the kinetic energy enters turbulence at the largest scales and is then transferred to smaller and smaller scales, until at the smallest scales the energy is dissipated by viscous action. Okay. So, that is the whole point. Okay. So, that kinetic energy enters turbulence at the largest scales and is then transferred to smaller and smaller scales, until at the smallest scales the energy is dissipated by viscous action. So, this concept was realized by Richardson actually much earlier than Kolmogorov, and he penned down this poem that big holes have little holes which feed on their velocity, and little holes have lesser holes, and so on their viscosity. So, it is a nice poem by which this this whole picture is essentially basically put in it's conveyed to the general audience. Okay. Now, then the question is that, then what is the size of the smallest eddies? Okay, are they universal in nature? Well, how can you relate the size of the smallest eddies to those of the largest eddies? As length scale increases, do the characteristic velocity and time scale increase, decrease, or remain same? These are important questions to answer. Okay. And the Kolmogorov hypothesis of local isotropy is these are now what we will do is that, so to understand these things, so we will introduce Kolmogorov's different hypotheses. Okay, basically we will introduce three hypotheses, and the first hypothesis is this Kolmogorov's hypothesis of local isotropy, and this states that at sufficiently high Reynolds number, the small scale of turbulent motion are statistically isotropic. Okay. and it can be revised to the state that at sufficiently high Reynolds number the small scale turbulent motions which are away from the walls are statistically isotropic. Isotropic means that you define a statistical quantity which is invariant upon translation and rotation of your coordinate system. Okay. So, that is what is isotropy. So, it does not have any direction sense. So, it is whichever direction you rotate it says the statistic stays same, that is very important. It is not the instantaneous field we are talking about, it is the statistical field we are talking about. Okay. So, but the scale has to be much smaller than the energy containing scales. So, that is important. So, you see that is what is very important here. So, this using this we can go to the second Kolmogorov's the first similarity hypothesis, and he says that in every turbulent flow at sufficiently high Reynolds number the statistics of the small scale motion, okay, this word is very important, the statistics of the small scale motion have universal form and that is uniquely determined by the kinematic viscosity and the turbulent kinetic energy dissipation rate. Okay, so, this is very important, that these small scale motions are independent of anything, are universal. So, these three words important: small scale motion, are universal and determined by kinetic energy or the kinetic energy dissipation rate and kinematic viscosity, but it is only the small scale motion or the large scale motions. Okay. And so, what does that mean? That means that small scale motion, if we consider the smallest scales of turbulence to be the Kolmogorov length scales and the smallest scales of velocity or the Kolmogorov velocity scales and the Kolmogorov time scales. So, we can only determine this from this quantity using kinematic viscosity and dissipation rate. So, by dimensional analysis kinematic viscosity has a dimension of meter square per second, it is essentially the same dimension of diffusivity, whereas epsilon is essentially has a unit of you see it is what it is essentially twice nu times Sij times Sij, right. So, this has units of meter square per second. So, this has units of meter per second times meter per second. Okay. Sorry, this is not meters per second. So, this is meters this is meter per meter second and meters per meter second. So, this cancels. So, this essentially has a unit of meter square per second cube. So, dissipation rate has a unit of meter square per second cube and kinematic viscosity has a unit of meter square per second. So, then and whereas this will have a dimension of meters, this will have a dimension of meter per second and this will have a dimension of 1 per second, have a dimension of second. So, if so, then we using these quantities how can we form these scales? So, this can be formed only if it is nu cube by epsilon to the power of 1/4. It is Kolmogorov velocity scale can only be formed if it is epsilon times nu to the power of 1/4 and tau eta it can be only formed as epsilon by dissipation to the power of 1/2. Right. So, that is the thing. This is how the different scales of turbulence are formed by eta, u eta and tau eta. Okay. So, these are very important things and these are essentially universal in nature. So, that is what Kolmogorov's claim is and it actually turns out to be true. Using this we can have a very well good definition of essentially what are the smallest scales of motion are, and but this has to be this is statistical in nature, which should not be confused with instantaneous observations. Okay. So, so far we have talked about that far from the walls small scale are isotropic, yes, and secondly he introduced the first similarity hypothesis. We said that yes, when the flow is at large Reynolds number. Okay. So, these are very important, all this hypothesis holds at very large Reynolds number. So, at large Reynolds number the statistics of small scale motion have a universal form and they are uniquely determined by kinematic viscosity and kinetic energy dissipation rate. So, he only talks about small scales. What happens at the intermediate scales? Okay. So, at the intermediate scale he says that in every turbulent flow at sufficiently high Reynolds number the statistics of motion of scale L, which is an intermediate scale, that is which lies between your largest energy containing scale L0 and the dissipation scale which is Kolmogorov length scale, which is far away from both. Okay. So, this intermediate scale L which is or this intermediate range of intermediate scale L which is far off from, which is far smaller than the energy containing scale which is of the size of the largest energy containing scale which is of the order of the say the jet width, and at the same time which is also much larger than the Kolmogorov length scale, they have a universal form and that is determined by turbulent kinetic energy dissipation rate only, and it is independent of kinematic viscosity. Okay. So, this is very important. So, the smallest scales are determined by kinematic viscosity and turbulent kinetic energy dissipation rate. Intermediate scales, which are smaller than the largest length scales or the hydrodynamic scales. So, let us call this hydrodynamic scale L0, which is smaller than hydrodynamic scales yet much larger than the Kolmogorov length scale. Those are determined by the turbulent kinetic energy dissipation rate only. Why is that so? Why did Kolmogorov say these things? What does it actually mean? Okay. And as you will see that the second hypothesis is useful in deriving a scaled relationship for the energy spectrum at the inertial range. So, this is what he is meaning. Okay. These are the largest scales like this. Okay. So, this is largest and this is smallest. Okay. In between you have this intermediate scales. So, what is happening is that, and this is the largest length scale, which is like the size of the combustor or the size of your pipe or something like that, L, which is the largest flow length scale. This is the large eddy length scale L0. So, through production turbulent kinetic energy enters into this flow at these energy containing scales, okay, through this production mechanism. You have already seen that. So, then what happens is that after this LEI, when it enters into the inertial subrange, okay, it's basically behaves like an inertial system where it is not acted upon by any external force. Okay. So, in this inertial subrange, you neither have the effect of viscosity, nor you have any kind of an other force. So, this behaves in a kind of an inertial manner. Okay. So, essentially these kinetic energy that comes in, okay, enters here, these travel through all this length scale until it is being dissipated here. Okay. And in this range there is no production, in these intermediate range there is no production. So, production is equal to 0, there is no dissipation in these intermediate ranges. Okay. Production happens at the largest length scale, dissipation happens at the smallest length scale. So, this full range is essentially behaves like a in a conservative manner, and actually it can be shown that the angular momentum is essentially constant and there is no external torque on these eddies. Okay. That can be shown, but we will not go into that. So, if there is no source or sink in these intermediate scales in terms of the energy flux, so it means that across the scales the energy turbulent kinetic energy flux at each given length scale remains constant, because this is the only point where it is actually coming in and this is the only point where it is being dissipated. Okay. So, this whole breakdown procedure is essentially inertial, okay, where this eddies break down and there is no source or sink in this. Okay. So, there is no production, no dissipation. So, the turbulent kinetic energy flux crossing the length scales remains constant. Okay. Now, then if you have a dissipation process at the end, so then it means that the rate, whereas this dissipation happens at the smallest length scales, then it means that the rate of the turbulent kinetic energy flux which crosses these different length scales must be equal to the dissipation rate. Okay. So, that a steady flow of turbulent kinetic energy across scales can be maintained. Okay. So, then it means this tau L, which is the transfer of kinetic of energy to successively smaller scale, that can be equated to the dissipation rate. Okay. So, that is why the dissipation rate is independent of the kinematic viscosity. So, that is why even though the dissipation itself is given by twice nu Sij times Sij, but the fact is that because dissipation is almost an identity, that dissipation can be equated to this transfer of energy across successively smaller scales, which is the transfer of turbulent kinetic energy across these small scales. So, this thing is essentially independent of viscosity. Okay. And because dissipation rate has to be equated to the to this transfer of turbulent kinetic energy, this transfer rate, this dissipation rate, it becomes essentially independent of viscosity, though it is, you see, it is explicitly dependent on viscosity through these things. So, it means that, so the only way that can happen is that that if you change the viscosity, this quantity also changes, adjusts in such a manner that this whole quantity becomes independent of viscosity. So that is the whole beauty of turbulence. Okay, that is the whole beauty of high Reynolds number fully developed turbulence. That production happens at lengths production is of turbulent kinetic energy happens at large length scales. Then this whole turbulent kinetic energy travels through these different length scales. Okay, and when it travels through these different length scales, there is no source of sink. There is no dissipation mechanism, there is no production mechanism at this intermediate length scales, which is the inertial subrange. So it is untouched, this flux is untouched. Okay, flux remains constant across different length scales, and then when it goes into the smallest length scales, it is essentially dissipated into thermal energy, and the rate at which this dissipation happens must be equated to the turbulent kinetic energy rate. Okay. So consider like a pipe. If you the amount by continuity equation, the amount of, if there is no mass generation or loss through the pipe, so the amount of mass you put in at one end must be the amount of mass flow rate at the other end. So it similarly that's the continuity, to maintain the continuity of turbulent kinetic energy is like which is happening through this pipe is across different length scales. So this turbulent kinetic energy is passing through this different length scales and is dissipated at the end, and this dissipation at the end therefore can be equated to the transfer, or this rate at which this energy is successively formed into small and small scales, and that is why this transfer rate becomes essentially independent of viscosity, because there is no viscous action in this one, and because the epsilon can be equated to the transfer rate, epsilon essentially becomes independent of viscosity. Okay. Though it is very paradoxical in the sense that it is essentially dependent on viscosity, but the fact is that this strain rates adjust in such a manner, and that is it depends on becomes independent of viscosity. Actually it can come out here also that why the small scales are formed. You see that in the large Reynolds number turbulence, suppose you consider make a flow more and more turbulent by reducing the viscosity. So this one becomes smaller. Okay. But the thing is that I mean for if the dissipation rate has to be essentially kept constant. Okay. So what will happen is that then this dissipation rate, if the dissipation rate has to be held constant, so then this Sij must increase. So what is Sij? Sij is nothing but the gradient of the derivatives of the fluctuating velocities, the strain rate. So that means the strain rates must increase. The strain rates can increase only by reducing your length scales essentially, and that is why that becomes the dissipation rate essentially remains the same, whereas your size of the scales becomes smaller and smaller. Okay. So that is basically the basic mechanism of turbulence. Okay. Now here we can estimate different length scales. How do we estimate the large this L length scale essentially the characteristic length scale in the inertial range. So we can define a correlation function to indicate the extent of interaction between eddies, and that is defined by this R11 XR quantity, which is this autocorrelation function, average of uxt times ux plus r, which is shifted at the same time, divided by the variance of u, and this is the autocorrelation function behaves like this. Okay. That is it is correlated at itself, but this correlation reduces. So that is the important point, that if it was turbulence was noise, then the autocorrelation function would have been a peak like this, would have been a delta function, which is not so. Okay. So this is then this becomes the length scale here Lk, and then this becomes the integral length scale, and we can define integral length scale L0 essentially as 0 to infinity R11 XR dr, and we can also identify a characteristic velocity fluctuation by essentially the RMS of velocity. Okay. So these are the definitions we will use later. So essentially for large Reynolds number, transfer of energy from large to small eddies is independent of viscosity nu for the range of turbulence, and that is the inertial subrange, and that is what we have learnt. And because the rate of energy transfer, you see that we have equated epsilon is equal to tau. Okay, and this tau at any length scale. Okay. Now what is tau? Tau is essentially we can equate it to like if it is entering into this eddy, so we can equate it to like turbulent, this is energy transfer rate, so it is essentially must have units of kinetic energy per unit time. So we can estimate this as u0 divided by tau 0, and tau 0 we can write it as L0 by u0. So we essentially can get u0 prime cube divided by L0. Okay. Whereas this is the RMS of velocity, this is the integral length scale, and this is essentially becomes this. But then we can actually write this as, we can write epsilon is equal to tau L is equal to u0 prime cube by L0. L0 is equal to u any length scale as long as it in the inertial range divided by L. Okay, or any length scale k L at any k. Okay. We can write this for any essentially any intermediate length scale, whereas Lk is basically lies between your L0 and eta. Okay. So, this is how this equation we can equate the dissipation rate to the turbulent kinetic energy transfer rate across different length scales. So, whatever this quantity, even if you define this at the large length scale, this is also equal to the same quantity at the small length scales, as long it is larger than the Kolmogorov length and smaller than the your L0 itself. So, that is the whole beauty of turbulence, and then using this we can essentially show that of course, we have also shown that the dissipation is essentially dominates at a small scale and the Kolmogorov length scale. Okay. Now, turbulent kinetic energy spectrum derivation. Now, one very important quantity in turbulence is the turbulent kinetic energy spectrum. Now, what is that? So, we can define instead of length scales, we can also define wave numbers, whereas wave numbers k is nothing but 2 pi times the characteristic length scale. Okay. So, this is the wave number. So, we need to define this quantity. We want to see how this quantity Ek E of k behaves, which is nothing but the d of small k by d of capital K. This is the turbulent kinetic energy and this is the wave number. Okay. Now, for that we can just do the dimensional analysis, whereas k has units of you see k has units of meter square per second square, whereas this capital K has units of 1 per meter. Okay. So, then this guy Ek has unit of essentially meter square per second square divided by 1 per meter. So, it is essentially meter cube per second square. Now, in the inertial range you have seen that the statistics will only depend on dissipation rate, and of course, this quantity can depend on k itself. So, Ek, so by Kolmogorov's second similarity hypothesis, Ek can only be a function of the turbulent kinetic energy dissipation rate and k. Okay. So, by dimensional analysis, let us say this is epsilon to the power of alpha and k to the power of beta. Okay. Now, this has units of meter cube second square, and okay, let us write down as this thing itself, meters cube second square, and this is units of meter square per second cube to the power of alpha, and this is units of meter to the power of beta. So, using this we can immediately derive two equations, two algebraic equations, that is for equating the dimension of meter. Okay. We get 3 is equal to 2 alpha minus beta, and 2 is equal to equating the dimension of second, we get 3 alpha. Okay. So, alpha is equal to 2 by 3. So, epsilon, the power of epsilon will be equal to 2 by 3. Okay. So, now if you plug in this, we can estimate beta. So, 3 is equal to 4 by 3 minus beta. So, then it means beta is equal to minus 3 here minus 5. So, it becomes essentially equal to minus 5 by 3. So, then it means Ak is nothing but the dimension is e to epsilon to the power of 2/3 times wave number to the power of minus 5 by 3. So, this is the origin of the famous minus 5 by 3 spectrum. So, you see we expect that in the inertial range the turbulent kinetic energy spectrum Ek should have a dimension of epsilon to the power of 2/3 and k to the power of minus 5 by 3. And does it really have it? So, actually it turns out beautifully to be so, and this is one of the famous results of turbulence, that in fully developed turbulence for different configurations, different things, channel, jets, etc. This is taken from Pope's book actually. So, this has a slope of, when you plot it in log scale, this has a slope of minus 5 by 3. Okay. So, this is the famous minus 5 by 3 spectrum of turbulence. Okay. So, essentially we have looked into this the whole spectrum and the whole dynamics of turbulence, how turbulence basically sucks energy from the mean flow and then converts into turbulent kinetic energy, and then how this turbulent kinetic energy will comes into turbulence at the large scales because of the mean velocity gradients and internal stresses, then how that cascades into the smallest scale where it is being dissipated. And while it travels to these different scales, we see that the flux of turbulent kinetic energy transfer rate remains constant, and because it remains constant, it can be essentially equated to the turbulent kinetic energy dissipation rate. And using Kolmogorov's first and second similarity hypothesis, we can find out, using Kolmogorov's first similarity hypothesis, we can find out the dimension or the equations for the parametric dependence of the Kolmogorov length scale, velocity scale, and the time scale on epsilon and dissipation rate. And using second similarity hypothesis, we can find out how this energy spectrum will look like. So that is all for fluid turbulence, and using this concept we will move on to turbulent combustion, and that we will take up in the next class. So until then, thank you very much.